Okay, so we're going to go over molecules and bonding now. And this is what go back. So this is what a molecule would look like, and this is the way that the different elements or different atoms bond in order to create those molecules. So we've learned that atoms, these would be individual atoms, just the H by itself would be an atom. The C by itself would be an atom, and when they bond together, it creates a molecule which gives different properties to those elements. Okay, so we have already talked a little bit about Bohr models. You guys had to make a Bohr model for your project. And the Bohr models, the first shell should all have, the most that they're allowed to have in the first shell is 2 electrons. And if you look at hydrogen, we know, helium, helium is in the noble gas column, and it only has 2 electrons. So those 2 electrons, those are the 2 valence electrons, which we've talked about needing 8 valence electrons. So helium is the only one that there's an exception. It still has its full shell because the first shell is only allowed to have 2. So 1, 2. So this would be its full shell. So helium would have a full shell. It's happy. That's why it doesn't want to bond with other elements. The second ring can have 8. So I want you to make sure you write this down. So this is a table to explain if you are making your Bohr model, this is how the electrons would go. So on the first shell, the first ring, you do 1 circle around the nucleus, you can have up to 2 electrons. The second ring, you can have up to 8 electrons. The third ring, you can have up to 8 electrons. Fourth ring, you have 18. Fifth ring is 18. 6 is 32. And then 7 is also 32. Let me just get that back up. Sorry, I closed it. All other elements have partially filled outer electron shells. So the only ones that are all the way full would be the noble gases, and we've learned that already. They all have 8 valence electrons, but if we're doing the Bohr model, these shell numbers would be all of the ones. I lost my mouse to show you guys. So these would be full shells for those the noble gases. Okay. So this is called the Octet Rule. The atoms tend to have, they want to have 8 valence electrons. We've talked about that. That was on your test. You guys should be familiar with that. And those 8, the group 8, remember we circled that number 8 in group 18 to say that that's how many valence electrons they are. So going with this rule, that's why those noble gases don't want to bond. They are happy. They have those 8 valence electrons that make them happy. So they are stable, like we've said. All right, this is a little blurry, sorry. We have also talked about drawing your Lewis dot diagram. That was another part of your project. So the way you would do your Lewis dot diagram, you write your symbol, and then you find out how many valence electrons there are. And the valence electrons we can determine by the numbers that we circled at the top of the column. So 1, 2, and then the 3 through 8 on the 13 through 18. And then you draw the little dots around. So for Cl, which is chlorine, that is in group 17. And we can see that we are missing 1 valence electron to make it a happy, stable 8. So it's going to want 1 more valence electron. So our Cl is going to want to bond with a metal in the alkali metal group, the first column, to make it happy. All right, so here's some examples of elements bonding. I'll just move this here so you guys can see. So we have H, which is hydrogen, and hydrogen wants to bond with Br, which is bromine. And we could see that we have 2, 4, 6, and bromine is in column 17. So it only has 7 valence electrons. Hydrogen has 1. So they're going to want to share. So they're going to bond right here where that red is. And we can see over here we have the H and the Br. So this is where the Lewis dot diagram comes in handy, is to show us how elements will bond. So here we have S, which is sulfur, and H again, which is hydrogen. Sulfur is in column 16. So we have 2, 4, 5, 6. So since we only have 6, we need 2 hydrogens to make it full. So we need 2 more valence electrons. So sulfur can bond with either an element in column 2, or, which is the alkaline earth metals, or it's going to bond with an element in column 1, or it will have to bond with 2 elements in column 1. So here we have them sharing, so the H and the S share here, and an H and an S share here, so we can see how they would bond together. And then nitrogens, let me move this, I can't really point. Let's see if I can get it out of there. Sorry. All right, so the nitrogens, again, nitrogen is in column 13, 14, 15, so it would have 5 valence electrons around each. So each of them will need 3 more valence electrons. So we can see that the red ones are the ones that they're going to be sharing. And in this case, this isn't the same kind of bond as the HBr and HS. We can see that there's 3 electrons that they're sharing. So we can see that first N, if you count the first 2 black ones, 1, 2, right? And then we count all the red ones. So this N is sharing all of these. So these are using all of these electrons. So we have 2, 4, 6, and 8. And then this N also has 8. So it's these 2, 4, 6, and 8. So that's how our Ns, our nitrogens in the atmosphere, are bonded. So they're not bonded the same where they're only sharing or using that 1 electron between the 2. They actually have 6 between the 2 that they're sharing. All right, so just another picture, another example of how we can use the Lewis dot diagram to represent the bonding. Water, H2O, so we have 2 H's and 1 O. Oxygen needs 2 more valence electrons, so the hydrogens share it, and we can see here. So another way to represent, instead of having the dots around, when we show that there's a bond, we use a straight line, and that straight line represents 2 valence electrons. So again, here we have the hydrogens and nitrogen. So when they bond, this straight line is only 2 valence electrons. So some of you, when you made your molecules, you noticed that there were 2 lines. So that means they're sharing 4 valence electrons between those 2. Some of them even have 3 lines, like we saw previously right here. I don't know if I can go backwards. So this would actually have 3 lines because we have the 6 valence electrons that they're sharing. So each line represents 2 valence electrons. All right, so valence electrons are usually the electrons in the outermost S and P subshells. For right now, we don't need to understand what the letters mean to the S and the P subshells. You guys don't need to know that, but going into high school, you will. So your high school teacher will explain that. I just want you to be familiar enough with the valence electrons, the Bohr model, and the Lewis dot diagram. So that way, when you go into high school, it is more of a review, and that would just be the next step, the levels. All right, so let's just to see which atom this is. So we can look at the atom, we can see the representation, we can determine what it is. So we can see that there's 2 electrons in the first ring, plus another 1, 2, 3, 4, it should be 8, 5, 6, 7, 8 on the next ring, so that's 10. And then we have 1 valence electron. So that means I should be looking in that first column, and it should have 11 electrons total, which means it will also have 11 protons. So the atomic number would be 11, which is sodium. And sodium is in the first column. nope, going the wrong way, sorry. So sodium is right here in the first column. All right, so again, we already circled these, so this should look familiar, but if you weren't sure about it, we have the number of valence electrons. We circled the numbers in the column. So we have 1, 2. This varies depending on the element, which is why we didn't do anything with the valence electrons down here. And then we circled the 3, 4, 5, 6, 7, and 8. And like I said before, helium is the only exception to the rule of 8 because helium only has 2 valence electrons, but its first shell is full. So its last shell, really. It's first and last because it only has 1 ring. So it's full. So helium is happy with just having those 2. It's stable. All right, so here is a question. I want you to try to think about the answer. So how many valence electrons does potassium has? Potassium is K, which is 19 on your periodic table. So it is right here. So we want to think how many valence electrons does it have? And if you said 1, then you are correct. So the answer is B. How many valence electrons does aluminum have? Aluminum is number 13, it's in column 13 also. Therefore, it should have 3 valence electrons. Metals tend to blank electrons and non-metals tend to blank electrons. Now, this was one of the questions that was on the alien periodic table, and I kind of went over that. So metals, they have fewer valence electrons, especially the first 2 columns, which is the ones that we know how many valence electrons they have. So we only have 1 or 2. So it's more likely that those guys are going to be giving away their valence electrons to share, to kind of give to a non-metal, which is over here, because they have more valence electrons. So they're bigger, they're fuller, so it's more likely that these guys are going to give or lose their valence electrons, and these are going to gain their the valence electrons from here. So that would be metals tend to lose and non-metals tend to gain. All right, so again, just looking at the valence electrons, this should be familiar. Lithium is number 3 on the periodic table. It is in column 1, so we can see 1, 2, 3 electrons total. That way I know that we're talking about lithium. The first ring is full with its 2, so there's 1 more and 1. Because it's in column 1, it has 1 valence electron. Fluorine is number 9 on the periodic table. It is in column 17. Therefore, it should have 7 valence electrons. And we can see it's already counted for us. 1, 2, 3, 4, 5, 6, 7. 2 on the first ring. And if we count total, 7 plus 2 equals 9. So there is our fluorine. So that is what our Bohr model would look like for fluorine. All right, so a molecule, this, is defined as a stable neutral group of at least 2 atoms in a definite arrangement held together by a very strong chemical bond. So the molecules are bonded together, and we just saw how we can use the Lewis dot diagram or even the Bohr model to determine how they're going to bond together. And they are stable because they have those 8 valence electrons that they are sharing. So each element, because they're sharing those electrons, they now have the 8, so they are happy. They're not looking for other elements. A chemical reaction can happen, though, where it will split the electrons, split the atoms rather, but they still want to join with other ones. So last year, you guys learned about cellular respiration and photosynthesis, and we learned that they are equal and opposite reactions. So what goes into one is what comes out of the other. So they are the same elements, same number of elements, same number of atoms for everything. And when they go in, a chemical reaction happens so that they split, but they still aren't happy. Now they're not happy, they're not stable, so they're looking for those other atoms to join with again, and the reaction causes them to join in a different way, but we still have the same number. I can't move it. Sorry. All right. So chemical bonds. There are three types of basic chemical bonds. We are only going to learn about two of them. So an ionic bond, a covalent bond, and a metallic bond. So ionic bonds are between ions, and they form ionic bonds, obviously. So remember we learned that ions are we learned that the electrons are negatively charged and protons are positively charged. Neutrons are neutrally charged. So when an atom gives away one of its electrons or multiple electrons, it now has more positives than negatives. So it is positively charged. When an atom gains some electrons, so the giving away would be the metals. So the metals tend to be positively charged, and the nonmetals, when they gain electrons, they will have more negatives than positives, so they will be negatively charged. A covalent bond is when the valence electrons are shared between atoms from either network of solids or molecules. So we'll see what that means in a little bit. So they are more between nonmetals, when the two nonmetals share. So it's more, they have an equal amount of electrons between both of them. So like when we saw the nitrogen sharing with each other, they're not going to have that negative and positive attraction. And the metallic bonds, like I said, we're not going to go over that. Okay, so for ionic bonds tend to be between a metal and a nonmetal. And one atom would be losing an electron, where another atom would be gaining an electron. So we can see here sodium chloride, the sodium becomes positively charged because it loses its electron. It gives this electron to this guy. And then chlorine gains an electron, so it becomes negatively charged. So we have a negative and a positively charged atom here, or molecule rather. All right, so I'm going to take a minute to go over the definition of an ionic bond. Again, you don't want to write everything down, just kind of take it in and then write down or draw a picture of what is the most important in this paragraph. So ionic bonding is the complete transfer of valence electrons between atoms. Because they're transferring, they are now bonded together. They're giving or taking an electron, so they're bonded together. So this type of chemical bond that generates two oppositely charged ions in ionic bonds, the metals lose electrons to become positively charged cations. So the way I remember a cation is you usually get happy if you see cats. Some people anyway. So cations make you happy, so they're positive. Whereas nonmetals accept the electrons, they become negatively charged, so they're anions. So usually an is like a prefix for like a negative, something negative. So like, so an would be your negatively charged ionic atom. So ionic bonds require an electron donor, often which would be the metal, an electron acceptor, which would be your nonmetal. So hopefully you guys can just draw a picture with that. You don't have to write everything word for word. Ionic bonding is observed between metals, is observed because metals have fewer electrons in the outermost orbitals. So by losing their electrons, these metals can achieve noble gas configuration. So the rule of octet, the Octet Rule. Similarly, nonmetals have close to 8 electrons in their valence shells, so they want to accept a few electrons to achieve their noble gas configuration. So in ionic bonding, more than one electron can be donated or received to satisfy the Octet Rule. The charges of an ion and cation correspond to the number of electrons donated or received. In the ionic bonds, the net charge of the compound must be 0. So net charge just means the total charge. So if we count up all the protons and all of the electrons, that they would cancel out. But if we look at a particular atom in that bond, we would see that one is a positively charged cation and one would be a negatively charged anion. All right, so again, NaCl, we see that Na has 1 electron in its outer shell, Cl has 7, so they want to bond together. All right, and here's just another example so we can see this wants to go here. This becomes positively charged because it's losing an electron. This becomes negatively charged because it is gaining an electron. And now they satisfy the rule, the noble gas rule of the octet rule. This is more, again, like high school, college level, so this isn't something we really need to look at, but scientists are able to use the periodic table, so we have different colors that would represent how attractive they are, so we can use electronegativity to determine how they are going to bond. All right, so question time. Which pair of atoms will form an ionic bond? So again, we want to be looking at our metals and nonmetals, and we want to see how many valence electrons each have. So lithium has 1, but neon is in our noble gas family, so they are not going to want to bond because that would equal 9. K is potassium, so that has 1. And Br is in 17, so they would most likely want to bond. So that would be 1. So B would work. K and CS. CS is in the same row. It's also in, not row, sorry, column 1. So they would only have 2 each, so they would not bond. They are both metals. S, sulfur, and Cl. They are right next to each other. They are both nonmetals. So S would have 6 plus Cl would have 7. So that would not work because that would be 13 and too many, not 8. So the only one that would work for this would be B. So again, I'm going to let you guys try to figure this out. And in a few seconds, I will tell you the answer. All right, so if you read through it, you would have noticed that we have table salt on there, which is NaCl. So NaCl is the only one that would actually form that ionic bond, and that's one that we've gone over a couple times already in the slideshow. All right, and an ionic bond would form between SC and F. So SC is in the third column, which is a transition metal, and fluorine is 17. So because we don't know how many valence electrons SC has, we are going to say that's false. All right, so predicting ionic bond formula. So for K and O, again, K is potassium, O is oxygen. So we want to think K has 1 valence electron. O is in the 16th column, so it has 6. So 6 plus 1 is only 7. We still need 1 more. So we want to think how many Ks or how many more valence electrons does oxygen need if it has 6, and it would need 2 more. Therefore, the next slide. Oxygen needs 2 more valence electrons. K has 1 to give, so we would have 2 Ks. So we need 2 Ks, which is potassium, 1 oxygen. So the chemical formula for this, whenever there's 2, we have the subscript that goes with the symbol. So that would be K2O. And we could see that we would have 2 Ks. Here's our empty valence electrons. This is where they would want to go. And K joins with O here. Okay, so another one, magnesium and nitrogen. So Mg is in the second column. It has 2 valence electrons. Nitrogen is in the 15th column, so it has 5. So if we're thinking about so we have 5 and we have 2. So we want to think, is that going to work? Or how would it be able to work? So I want you guys to try to think about this on your own for a few seconds. How many more does nitrogen need? All right, so we know that nitrogen needs 3 more because it has 5 valence electrons. And magnesium has 2 valence electrons to give. So each of them needs to give 1.5, so we would need 2 magnesiums to give, let me rethink this or rephrase this. So we would need to have more nitrogens and more magnesiums to equal. We need to keep going until we get the total of 8 for everybody to be happy. So nitrogen would end up having 3, would need 3, one single one would need 3, one single magnesium would need or have 2 to offer. So that, like I said, we are off by 1. So we would need to add another nitrogen in. So now we have 2. So 2 would need 6. So 2 nitrogens would need 6 more valence electrons to be stable. And we can do that with magnesium because magnesium offers 2. So that would be, we would need 3 magnesiums to equal 6 valence electrons to donate. So we would have the 3 open valence electrons in the first nitrogen, the 3 open valence electrons in the second. So they would all bond together because we would have 2 magnesiums for 1, 2 valence electrons from 1 magnesium for 1 nitrogen, 2 for another one, and then a magnesium to share between the 2. So you can see that over here. All right, so another way to think about this is to find the formula. Once you know what the ionic charges are, write down the ionic charges. So we know that Mg would be plus 2. That means that it has 2 more protons than it has neutrons. Electrons. Nitrogen would be gaining 3. So that would be a negative 3. And then we would cross it until we, so that the 2 goes down for the nitrogen. So that means that the 2 is being given to the nitrogen and the 3 is being given to the magnesium. So this is how we write the formula, Mg3 N2. So this is just another way to think about it when you're writing a chemical formula. Okay, so that was all ionic bonds. That's where we share, we give or one electron or electrons, and we either gain electrons or we lose electrons. So that's where we have the negative and positive. Covalent bonds form when the electrons are actually shared between the 2 or 3 or however many atoms there are. So since electrons move very fast, they can be shared and effectively fill the empty outer shell. So this looks like it's actually 2 hydrogens sharing their electrons to make the 2. And remember, 2 hydrogens sharing the electrons would make that first ring full. So that would be stable. So covalent bonding is sharing of electrons between atoms. This type of bonding occurs between 2 atoms of the same element. So we have nitrogen, oxygen, we just saw hydrogen, for example. Or elements that are close to each other in the periodic table. So the bonding usually happens between nonmetals, but it can be observed between nonmetals and metals. So usually we're going to see more of the nonmetals joining, just like I said. Hydrogen is a nonmetal, even though it's in the first column. Oxygen, we know, in the atmosphere is O2. Nitrogen in the atmosphere is also O2. Fluorine, chlorine, those would also bond with themselves. All right, so here's an example where they don't really have, chlorine has 7 valence electrons, and P is phosphorus, and it has 5 valence electrons. So they don't have few enough to give away. So they are going to be sharing their electrons. So they don't have like 1 or 2 to give away. So they're going to be a covalent bond. So we can see how they would join together here. All right, so that is it for the notes. We are going to move on to some of the videos now. So we have how to make new molecules. So we just saw how molecules are made from the bonding, and we can determine how they're bonded. We can also determine how to write their chemical formula. So these we are going to do as a class a different time.